Imagine you've trained a language model with 175 billion parameters. It cost you millions of dollars and weeks of compute. Now a customer wants a version customized for legal documents, another wants one for medical notes, and a third wants one for SQL generation. Under the traditional recipe, you'd fine-tune the entire model 3 separate times, producing 3 complete copies, each weighing in at 350 gigabytes. Storing them, swapping between them at serving time, and even just having enough GPU memory to update all those parameters during training becomes a nightmare. This is the practical pain point that motivates the paper we're looking at today, which introduces a technique called low-rank adaptation, or LoRA. The core problem is that fine-tuning produces an update to every weight in the model, and that update is just as large as the model itself. Researchers had been trying to make this cheaper for years, mostly along 2 lines. The first was adapter layers, which means inserting small new neural network modules between the existing transformer layers and training only those small modules. The second was prompt tuning, or prefix-tuning, which keeps the whole model frozen but learns special trainable tokens that get prepended to the input. Both approaches save parameters, but each has a real cost. Adapter layers, even though they're small, add sequential computation to every forward pass, which actually hurts inference latency in the worst place possible, which is small batch online serving. The authors show that on GPT-2 medium with a batch size of 1, adapters add 20 to 30% latency even when they have under 1% of the original parameters. Prefix tuning, on the other hand, eats into your sequence length because those learned prefix tokens occupy positions you could have used for actual content, and the authors found it's also just finicky to optimize, with performance that wobbles unpredictably as you change the number of trainable parameters. The key insight that motivates LoRA comes from earlier work showing that large, pre-trained models, despite having hundreds of billions of parameters, actually live on a surprisingly low-dimensional manifold. The authors hypothesize that if the model itself has low intrinsic dimensionality, then the update you apply during fine-tuning probably does too. In other words, when you're nudging a pre-trained model to be good at SQL generation, you don't really need to move it in billions of independent directions. A handful of directions might suffice. Think of it like adjusting a piano that's already mostly in tune. You don't need to retune every string from scratch, you just need a few small, targeted tweaks. Here's how LoRA actually works. For each weight matrix in the transformer that you want to adapt, instead of learning a full update matrix of the same shape, you parameterize that update as the product of 2 much smaller matrices. If the original weight is a square matrix that's, say, 12,000 by 12,000, the update is represented as one matrix that's 12,000 by R multiplied by another that's R by 12,000, where R is the rank you choose, often something tiny like 4 or 8. The original weight stays completely frozen, and only these 2 small matrices get gradient updates. At the start of training, one of them is initialized to 0 so that the effective update starts at exactly 0, meaning the model behaves identically to the pre-trained version until training nudges it. There's a scaling factor that divides by R, which lets you change the rank without having to retune your learning rate. Now here's the elegant part. Because the update is just a matrix that gets added to the original weight, you can, at deployment time, simply compute the sum once and store a single merged weight matrix. That means at inference, LoRA looks exactly like the original model. 0 extra latency, 0 extra compute, 0 architectural changes. And when you want to switch to a different task, you subtract the current LoRA update and add a different one, which is a fast operation involving only the tiny adapter matrices. In their GPT-3 experiments, they apply LoRA only to the query and value projection matrices in the attention layers with a rank of 4, which gives them about 35 megabytes of trainable parameters per task instead of 350 gigabytes. That's a 10,000-fold reduction in checkpoint size. GPU memory during training drops from 1.2 terabytes to 350 gigabytes, mostly because the optimizer doesn't need to maintain momentum and variance estimates for the frozen weights. The empirical results are striking. Across RoBERTa, DeBERTa, GPT-2, and GPT-3, LoRA matches or beats full fine-tuning on benchmarks like GLUE, E2E, NLG, Wiki-SQL, and Samsung. On GPT-3 with Wiki-SQL, full fine-tuning hits 73.8% accuracy with all 175 billion parameters trainable, while LoRA hits 74% with only 37 million trainable parameters. On multi-NLI, LoRA edges out fine-tuning by about 2 points. And importantly, prefix-based methods actually get worse as you add more parameters past a certain point, while LoRA scales gracefully. Then comes the part of the paper I find most intellectually interesting, which is the analysis of what these low-rank updates actually look like. The authors compare adaptation matrices learned with rank 8 versus rank 64 and find that the top singular directions overlap heavily, while the rest is essentially noise. They even show that rank 1, just a single direction of update, gets you most of the way there on these tasks. That's a stunning claim, suggesting that adapting a 175 billion parameter model to a new task might only require pushing it in a single carefully chosen direction in weight space. They also analyze the relationship between the update and the original weight matrix. The update isn't aligned with the dominant directions of the pre-trained weight, but rather amplifies directions that were present in the pre-trained model but suppressed or underweighted. The amplification factor is huge, roughly 20 times. So fine-tuning, at least in this view, isn't teaching the model new things from scratch. It's turning up the volume on latent features the model already knew about but wasn't using for the general pre-training objective. Of course, there are limitations worth being honest about. Batching inputs from different tasks in the same forward pass becomes awkward if you've merged the LoRA weights into the base model, because each input would need a different merged matrix. You can avoid this by keeping the adapters unmerged and selecting them per sample, but then you give up some of the latency benefit. The authors also only adapt attention weights, leaving MLP layers, layer norms, and biases untouched, which they acknowledge as future work. And the claim that very low ranks suffice is shown empirically on specific tasks, with the authors themselves noting that adapting to a radically different language or domain might require much higher rank. Now let's walk through some questions you might have after hearing all of this. You might be wondering, why is it okay to initialize one of the two matrices to 0 and the other to random Gaussian noise, instead of initializing both randomly? The reason is that you want the model to start out behaving exactly like the pre-trained model, so the effective update needs to start at 0. If you initialized both matrices randomly, you'd be injecting random noise into the model's weights from step 1, which would degrade its behavior before training has even begun to find useful directions. By zeroing one matrix, you guarantee a clean start while still allowing gradients to flow and push the matrices into meaningful values. Another natural question is, why does adapting just the attentions query and value matrices work so well, instead of also adapting the MLP layers, which contain way more parameters? The authors don't claim this is optimal, just that under a fixed parameter budget, spreading adaptation across multiple attention weight types with lower rank beats, concentrating it in fewer weight types with higher rank. The intuition is that the attention mechanism is what controls how the model routes and combines information, so small shifts there can substantially reshape the model's behavior for a new task without needing to retrain the underlying feature representations stored in the MLPs. And one more, if low-rank updates work this well, doesn't that suggest something deeper about how fine-tuning actually works? Yes, and this is one of the most thought-provoking implications. The fact that a rank 1 update can meaningfully adapt a 100 billion parameter model, combined with the finding that the update amplifies existing but suppressed directions in the pre-trained weights, suggests that fine-tuning isn't really teaching new capabilities. It's more like adjusting which capabilities the model emphasizes. The pre-trained model already contains the knowledge needed for downstream tasks, and adaptation is essentially a routing problem, not a learning problem in the deep sense. For large-scale recommendation systems, LoRa's ideas translate quite directly to several real production challenges. Consider that modern recommenders often use large transformer-based encoders for user sequences or item embeddings, and you frequently want specialized versions for different surfaces like home feed, search, ads, and notifications, or for different countries, languages, or user segments. Rather than fine-tuning and storing a full copy of your billion-parameter user encoder for each surface, you could keep one frozen base model and train tiny LoRA adapters per surface. This dramatically reduces storage costs, makes A/B testing of model variants much cheaper because experimental adapters are megabytes instead of gigabytes, and enables fast rollback since swapping adapters is nearly instantaneous. The zero inference latency property is especially valuable for ranking and retrieval, where you're often serving under tight tail latency budgets at high QPS. You can merge the adapter into the base weights at deployment time and pay no runtime cost relative to a single shared model while still getting per surface or per segment specialization. And the multi-tenant story is compelling too. Imagine offering personalized embeddings where each large advertiser or each major content partner gets their own LoRa adapter trained on their specific objectives, all sharing the same frozen foundation model in GPU memory. This becomes operationally feasible only when the per-tenant footprint is tens of megabytes rather than hundreds of gigabytes, which is exactly what LoRa delivers.